terrestrial ground, there have been experiments trying to distinguish between the two. But unfortunately, the fields required for nonlinear effects to be created and the precision of the instruments are not compatible. They cannot give definite results on the terrestrial program. You were saying, in the astrophysical regime. In the astrophysical regime, yes, potentially we could distinguish between Maxwellian and non-Maxwellian. The problem with it is that we lack information. Because let's take, for example, what I did with electromagnetic shift. Okay, there we have the redshift for a particle coming from. Okay, it's not a matter; it's a simple dipole. But in principle, we can make a more elaborate model and have it modelized amount. Let's say, okay, and we have a definite number for what the electromagnetic shift due to only to the nonlinearity force. The problem is that from the magnetron, we don't know the frequency at which the photon is emitted. So, an experimentalist only measure, the distance, but he measures the redshift. But inside the redshift that he measures, what is the electromagnetic part? What is the gravitational part? What is the part due to rotation? This is the point that we cannot distinguish inside the measurements. That's the big problem, because we have definite results for the nonlinear parts, but in practice we cannot distinguish the nonlinear part from the gravitation, and therefore there are no conclusive evidence that Euler-Heisenberg theory or Bonetti theory is valid or not valid. That's simply the point. Because theoretically we can perform the computation, but experimentally we cannot distinguish between the two cases.
But that's the feature of the Bohr-Info theory? Or?
No, this is in general the problem with nonlinear theories. Because, like I said, the regimes in which the nonlinearities give actually measurable effects are extreme. So, on Earth, when you reach those, you can reach those regimes in a lab, but in those regimes, the instruments are not accurate. In the astrophysical regime, the instruments are accurate enough, but you cannot distinguish within the measurement if your effect is due to nonlinearity or simply gravitation.
But my question was in the sense that there is a way that I can analyze my gravitational theory to say that's Bohr-Info, that's general relativity.
But this is Bohr-Info dynamics. I'm not. I know that there is Bohr-Info gravitational theory, but here I'm applying Bohr-Info electromagnetic theory to Einstein relativity.
Cosa serve? Lui I mean, what you have, I know that your second program that you showed the radiation in the Bohr-Info case is a program in progress. But your final goal is to get something like the Larmor expression for the power irradiated as being proportional to some power of the acceleration.
Yeah.
This is what you have in mind to get at the end of the day. No?
Yeah, that would be ideal. Actually, what we would love to achieve would be to calculate the addition reaction. Originally, we had much more ambitious plans because, like I said at the beginning, the Bohr-Info part, what we can do, what we can imagine, because of Bohr-Info theory smoothing the divergence of the origin, even the radiation reaction doesn't need to be normalized. But unfortunately, we were not able to solve the problem non-perturbatively. we had to make an experiment. We had found a way to actually write down the equation in a non-perturbative way, because this problem, I said it 3 times already, has axial symmetry. So basically you can think of it as a bidimensional problem. And an Argentinian guy named Ferraro wrote some article where they actually propose to a solution for Born dynamics in each dimension. And in those, they use this one form and two form theory, and they are able actually to find a closed form in terms of forms for the field. The problem with it is that you need a seed. You need to make a guess on the one of the forms inside this expression, and if you get this right, you can compute the field. These seeds have been computed within the Maxwell theory, but in Cartesian coordinate, not in Riemann coordinate. We tried to move it to the Riemann spacetime, but once we did so, the equations for the seed were too complicated to solve, and we could not perform. We could solve it numerically, but numerically we did nothing. So, because actually, unfortunately, even if we succeed in computing the integral, this integral here, what happens is that we are going to have always the divergence coming from this here, because the solution, the full solution, would be this thing here plus what we get from this. And this thing here is obviously similar, like because this is a Maxwellian field. The point is that we truncated the series at the second order essentially. If we could sum up all the series, the result should be smooth, should be regular. But truncating the series, of course, we don't obtain what we want, a regularization of the dissociation. But this is the best that we can do because. Like I pointed out at the beginning, actually, this linearity here is actually a terrible nonlinearity because it comes inside the parentheses and inside the derivation, and it's a square root of the modulus of the field square. So,
I have a question. Curiosidade. You said that there are 2 main extensions of Maxwellian theory. You said nonlinearity and massive photon.
yes.
If we have both.
You mean massive and nonlinear?
Yes.
Yes,
Because
it is possible.
you said that in the mass, in the electric point, we have a singularity. And if the photon was massive, we have some much singularities than we want. And then não consigo expressar. Você pode explicar melhor?
O que você quer dizer exatamente com a massa do fóton na questão da singularidade? I try to get from him and explain to you.
Por exemplo, ele está falando que no caráter não linear a gente tem uma singularidade no elétron por causa da massa dele. Eu falei, agora se você junta o segundo tipo de teoria que admite um fóton massivo, você teria uma singularidade para cada parte, para cada fóton que você tivesse. Então, se você tem um plano propaganda, você quantizasse, você teria mais singularidade do que a gente poderia, mas será que a gente consegue trabalhar com isso?
Você junta a massividade,
o fóton massivo e a não linear, exatamente.
Como isso afeta a estrutura de singularidade.
Como é que a gente vai ter propagação? Como é que a gente vai ter interação eletromagnética se tem uma singularidade em cada fóton?
So what he's saying is that if you combine massiveness of the photon plus non-linearity, you perhaps change your structure of singularities. So he's asking himself, or he's asking to you, if you have some thoughts about how the photon, if you have singularities every time you emit a photon, how you understand the radiation of electromagnetic radiation from the child?
The question is actually more complicated than that even, because to my knowledge, the only context within I've seen a massive photon with nonlinearity is the one that I'm working on with Professor Layel, and it comes from the breaking of fundamental symmetry, of Lorentz and SUSY symmetry within the supersymmetry context. Therefore, even the interpretation of the radiation must be carefully analyzed. And actually, the collaboration has not progressed enough for me to give you a clear answer to it. I'm sorry.
No, very good. Thanks.
Another question. Do you think that the Riemann gauge bursts are a situation for nonlinearity or not?
This is an excellent question. Because there are polarizing theory, for example, gives beautiful news. Okay, so we have expression relation for a photon of different frequencies, and gamma burst doesn't measure a particular frequency. Expression relation for what is it even for regular pulsar? It doesn't measure expression relation for the photons. And the problem is the same that I told you before. We cannot distinguish between because you can attribute that dispersion relation also to the interstellar medium. In the interstellar medium, even if it's very rare, it affects the propagation like a medium and slows down some photons and more with respect to others according to the frequency. And therefore, you cannot distinguish between these two effects. And again, you have the same problem that. But in principle, yes. In fact, during my stay here in Brazil, I found a couple of articles that are quite interesting, in which the authors compare the gamma ray burst dispersion relation to the quantum gravity dispersion relation. Of course, this is not quantum gravity; has nothing to do with what I did here. But if we could actually explain the quantum gravity effect for all the propagation of photons with the nonlinearity in the theory instead of quantization of the gravitational field, then we would have a comparison between the two. But this is just an idea I have. I cannot show you an equation to sustain my thesis. This is just my intuition.
In a simple thought, do you think that when the energy increases, the possibilities of nonlinearity also
increases?
This is the general thought.
In general terms, the higher the energy, the higher the probability that you can see nonlinear effects. Yes. In fact, in terrestrial laboratories, what you do to investigate nonlinear theories that you go very, very close to the nuclei. Okay, nowadays there are very strong magnets, so you can try and create some very intense fields, some very localized and intense fields. But historically, the way that people try to investigate this nonlinearity is going very, very close to the nuclei. The closer you go, the stronger the effect is, of course. It's just like scattering, for example. You see that the beyond the level arise, the closer you go, the faster you shoot your test particle. That's exactly the same.
Because if you go to high energy, it's not, the higher is the energy, the closest you are to the field theoretical limit, And
Exactly.
theories, quantum field theories are all nonlinear. So if you are at very high energies, unavoidably you attest matter in the limit where the matter behaves under the laws of quantum field theory. The quantum field theories are all nonlinear. Quantum electrodynamics is completely nonlinear. So the more fundamental level of the matter is really nonlinear. So you expect nonlinearity, as much as the energy is high.
So another question, about the nonlinearity in photonics. Photonics there's a large spectrum of information. Just the photon and not necessarily connected with the electric charge. How do you see the possibilities of non-linearities in photonics? You know,
I'm not an expert, I cannot answer this question. So, I mean, I'm not enough inside, I do not have enough knowledge of photonics to give a reasonable answer.
So, okay, Chico.
You said that when I asked that there is no curvature, but when you are talking about astrophysical tests, you're still talking about tests that are low curvature tests, or non-curvature tests.
No, wait a second. What I said that there is no curvature when I write down the linear metric. But if you perform a statistical test, of course there is a curvature.
So you correct the metrics, so it's according to the space time.
Wait a second. Here, what I did is simply trying to compute the field of an isolated particle. I mean, let's take a space in the universe that is far away from any relevant gravitational field. You can approximate the space as a Minkowski, and you have a particle that accelerates at the particle. If you want to apply Born-Infeld theory within the gravitational context, of course you must take into account the metric. That is obvious, but that's not what I try to do here. As you saw, already the Minkowskian case, the problem is mathematically complicated enough. If you add the curvature of the space-time, I don't think that you have many chances to solve the problem. I mean, you can give it a try if you want, but I would be very happy if I could solve what in the Maxwellian case.
I just think that at high curvatures, if it were possible to solve the problem, you should, in theory, could see the difference between gravitational effects and electromagnetic effects in high curvature scenarios. But
Yes, that would be very nice. I agree.
Okay. So, Luca, thank you so much. Grazie infinite. We are very happy about the talk. So, next time, come back and we'll do a Luca.